Here are some examples of improper integrals. It can be improper because one of the integral limits is infinity or minus infinity, or it can be improper because the limits make the function undefined. So let's see what type this is. We have here 1 to infinity. So what's going on here is, as this upper limit is going to infinity. Well, we can try 10. That's not anywhere near infinity, but it's a pretty large number. It makes this denominator equal to 1,000. Anyway, when you do Simpson 100, you get 0.495. If you increase the upper limit going toward infinity to 50, you get 0.49999. That's with Simpson 200. We have a little limitation on our calculator because 200 is really not enough because we're getting large numbers here. There's not enough sub-intervals, but if we get too much higher than 200, our little calculator is going to stall, and you're going to be sitting there for 10 minutes, and you don't want to do that. So the question is, will the answer limit out to a value, or will it keep creeping up and eventually go to infinity? The area we're talking about, as far as on the graph, 1 to infinity, is all this area here, going all the way out under this curve forever and all adding up. So the question is, does it add up to something, or does it creep up to infinity? So the way you do that, the normal trick of the trade, is to write this integral where you have the letter b up there, and that's just a finite number. So you work out that integral, you get this, you evaluate it, you get this, you get this, and that simplifies down to here. So here's the integral from 1 to b. Your improper integral is defined in this case as the limit as b goes to infinity of the integral of 1 to b of the integrand there. So that's what that notation really means. This infinity is really not even proper to put there, but you can certainly put b and then let the limit as b goes to infinity. Then that equals what it was simplified to earlier. And as you can see, as b goes to infinity, this b squared gets very large, going to infinity. Negative 1 over infinity is going to 0. So this limit goes to 1/2. And that's what our decimal numbers showed that they were approaching here. So that matches up. So this integral is said to converge or converges, and it converges to 1/2. Now we have another example here. Same function, but now the integration limits are 0 to 1. Well, at 0, the function is undefined. So that's what makes this improper. And here's the picture. So the question is this curve slammed up against the y-axis enough so the values that are adding up there are small enough to converge the sum? It looks pretty far away as it's going. It's going toward the y-axis very slowly as it goes up. So our suspicion is that this area is going to add up to infinity, but let's see. Because it keeps going, the function keeps rising. Okay, so do our usual trick. The trouble is over here where it's 0, so we put the b there, The integral is this. Evaluating it out gets this, simplifying down to here. So now our original integral is the limit as b goes to 0 from the plus side. We could just say 0, but we're really going down to 0 because the interval goes from 0 to 1. So we're not concerned with anything below 0. So I might as well put in plus. That might matter. Then put the b there. Then put in what that integral b to 1 was equal to. And as b goes to 0, this is 1 over 0. That's going to infinity. So the negative 1/2 is going to not affect it. So that goes to infinity, which means that the limit doesn't exist, which means that the integral does not exist, which it means the integral diverges. In other words, the area adds up to infinity. Okay, next example. Here's your graph of 1 over square root of x. The question is 1 to infinity going to converge or diverge? Well, this side of the curve is converging up to the y-axis pretty quickly, but this side, which is what we want, is converging down rather slow. So our suspicion is that this area is going to just keep on adding up too much, and it's going to go to infinity. So let's see. You put the b in place of where the infinity was, and work that out. Work it out. Simplify it down to here, and then go to our original integral. 1 to infinity is equal to this limit, and that is equal to this. And when b goes to infinity, this is going to infinity, and minus 2, which doesn't affect it. So it's going to infinity, which means it doesn't exist. So the integral diverges. So there's just too much area adding up in here. And then another example here. 0 to 1 of that 1 over square root of x function. So this is the area we're talking about. So that function does die into the y-axis asymptotically pretty quickly here. So this has a chance to converge. Trick of the trade is, 0 is where the trouble is, because that's where the function goes to infinity. You can put in a small number almost to 0, but to the right, and get a sense for what the integral is going to do. This integral evaluates out to 2.0756 using Simpson 100. So let's just see. So now we do our integration with the b down here. Comes out to be 2 minus 2b to the 1/2. So when you do your original integral, your limit notation, b goes to 0 from the plus side. So this is going to 0. So square root of 0 is 0, so it's just going to be 2. So indeed, the integral converges to 2, and that matches up to what the integral was, the Simpson rule said.